actually. I was here. Okay. All right, sorry about this. Yeah, so I was saying, so one of the interesting things that came up from this analysis was that, which was initially a bit surprising, was that not only these variable diffusion models, so where we actually explicitly introduce this density-dependent diffusion, show a push wave, but also the ones that don't have it, which was, why is that? I mean, we didn't put any variable, any density-dependent diffusion, so why does that happen? Well, the reality is that there are actually two mechanisms that are very different in origin that generate this variable density dependent. One is this explicit effect that I described at the beginning due to simple steric interactions. So the more hosts we have, the more difficult it will be for a phage to actually disperse through this crowded environment. The second one, which we call implicit effect, is actually due to the infection dynamic, and it's due to the fact that the virus, while it's infecting the host, it's not capable of diffusing. So it's actually trapped for a certain period of time, tau, inside the host, unable to diffuse. And with a simple, well-mixed argument, one can show that also this hampering effect is density dependent, obviously. So the more bacteria we have, the more the virus will be trapped. All this basically can be captured, can be shown directly. So in the UDM model or plus model, we also have this density dependent diffusion because of this implicit effect. So even if there's no variability in diffusion due to this steric interaction, if we introduce that, we can just multiply this effect by the boost due to the steric interaction, and we get something much higher. If we now move to the right, so we actually account for the fact that infected cells may not absorb viruses, then what effectively we do is that we shift this implicit effect more to the right, because now only the free bacteria will be able to absorb the host. So they will trap the virus, will absorb the virus, so they will trap the virus here. Instead, the infected bacteria won't do this. And then obviously if we account for the two, we get the product. So that's where we get the broader region of infection. All right. So with this, I'll just summarize. I'm sorry that I ran a bit late. And so I hope I showed you, even if very quickly, that these viral expansions undergo this density-dependent diffusion, which in certain regions, which are quite relevant for, especially in experimental conditions, can give rise to traveling waves. And that this density dependent has two very independent origin. One due to the steric interactions, excluded volume interaction between virus and host in this crowded environment, and the other due to the fact that there is this incubation time in which the virus is stuck inside the host. Something that we're very excited is that we, my talented postdoc very recently managed to engineer two phage strains that induce either red or green fluorescence in the infected host, which allows us actually to track genetic diversity as the virus expands. And here is an example of these pictures. And I'll stop here and take any questions.